Remember, velocity is defined as the time rate of change of position. What this means is if we integrate both sides with respect to time, we get an expression that says the integral with respect to position is equal to the integral with respect to time of our velocity from t naught to t. Well, the left-hand side of this just becomes our position function minus our position at time t equals t naught. And the right side is our integral from t equals t naught to t of our velocity with respect to time. This means that our position function is equal to our initial position at time t equals t naught plus the integral with respect to time of our velocity. Remember, our velocity has an x component equal to v naught cosine theta naught I hat and a y component equal to v naught sine theta naught minus gt. So our initial position plus, and let's distribute this integral through. So we're going to integrate three terms. One term for the x component and two terms in the y component. When we integrate the x component, we get v naught cosine theta naught t. This is because v naught and cosine theta naught are constants. That's for the x component. For the first term in the y component, we get v naught sine theta naught t, because v naught and theta naught are constants with respect to t, minus 1/2 gt squared. And this both components are evaluated from t naught to t. So this is the initial position vector plus v naught cosine theta naught evaluated between t and t naught. This is the x component plus v naught sine theta naught evaluated from t to t naught, or t naught to t rather, minus 1/2 g t squared minus t naught squared. And this is for the y component. Now remember, t naught is equal to 0. So that means this expression in the y component, both of these expressions are equal to 0, as well as this expression in the x component is equal to 0. What we have then is our position as a function of time is equal to our initial position at time t equals 0 plus v naught cosine theta naught t for the x component plus v naught sine theta naught t minus 1/2 gt squared for the y component. Well, remember, the initial position was given as x naught I hat, so some initial position along the x-axis, plus y naught j hat. This means that our position as a function of time is equal to x naught I hat plus the y naught j hat plus v naught cosine theta naught t I hat plus v naught sine theta naught t minus 1/2 gt squared for the y component. So let's collect the terms together. For the x component, we have x naught plus v naught cosine theta naught t. And for the y component, we have y naught plus v naught sine theta naught. It looks like I forgot a t from here. Let's backtrack. Let's look at the previous page. Yes, I forgot to write down a t for that portion of the y component. So going back to our current page, this should be a t right here, minus 1/2 gt squared as our y component. We now have an expression for the position of an object as a function of time when it is in free fall. We also have an expression for the velocity of an object as a function of time when it is in free fall. Now remember, free fall is the state in which the only force acting on an object is the force of gravity. Here, the only component of velocity that changes with time is the y component. Given these two results, which I will call the first and second kinematics equations of motion, we're able to predict the future path of any object as long as they are under the influence of one and only one force, the free fall acceleration due to gravity on that object, or rather, as long as they are under the influence of one and only one force, gravity. And if the force of gravity is constant in a uniform gravitational field, such as we can model when we're close to Earth's surface, then these two functions can be used to predict the motion of that object.